In this chapter we focus on the functional groups. Families of organic compounds. Organic compounds can be grouped into families by their common structural features. We shall survey the nature of the compounds in a tour of the families in this course. Functional group is collection of atoms at a site within a molecule with a common bonding pattern. The group reacts in a typical way, generally independent of the rest of the molecule. For example, the double bonds in simple and complex alkenes react with bromine in the same way. Compare ethylene, a plant hormone that causes fruit to ripen, with methane, a much more complicated molecule found in peppermint oil. Both substances contain a carbon-carbon double bond functional group, and both therefore react with bromine in the same way, to give products in which a bromine atom has added to each of the double bond carbons. Look at table, which lists many of the common functional groups and gives simple examples of their occurrence. Some functional groups have only carbon-carbon double or triple bonds, others have halogen atoms, and still others contain oxygen, nitrogen, sulfur, or phosphorus. Table 3.1 lists a wide variety of functional groups that you should recognize. The functional groups affect the reactions, structure, and physical properties of every compound in which they occur. Types of functional groups: multiple carbon-carbon bonds, alkenes, alkynes, and aroms, aromatic compounds, all contain carbon-carbon multiple bonds. Alkenes have a double bond, alkynes have a triple bond, and aroms have alternating double and single bonds in a six-membered ring of carbon atoms. Because of their structural similarities, these compounds also have chemical similarities. Functional groups with carbon singly bonded to an electronegative atom. Alkyl halides, haloalkanes, alcohols, ethers, amines, thiols, sulfides, and disulfides. Alkyl halides have a carbon atom bonded to halogen. Alcohols have a carbon atom bonded to the oxygen of a hydroxyl group. Ethers have two carbon atoms bonded to the same oxygen. Amines have a carbon atom bonded to a nitrogen. Thiols have a carbon atom bonded to the sulfur of an SH group. Sulfides have two carbon atoms bonded to the same sulfur. In all cases, the bonds are polar, with the carbon atom bearing a partial positive charge, and the electronegative atom bearing a partial negative charge. Groups with a carbon-oxygen double bond, carbonyl groups. Carbonyl groups are present in the great majority of organic compounds, and in practically all biological molecules. These compounds behave similarly in many respects, but differ depending on the identity of the atoms bonded to the carbonyl group carbon. Aldehydes have at least one hydrogen bonded to the CO double bond. Ketones have two carbons bonded to the CO double bond. Carboxylic acids have one carbon and one OH group bonded to the CO double bond. Esters have one carbon and one ether, like oxygen, bonded to the CO double bond. Amides have one carbon and one nitrogen bonded to the CO double bond. Acid chlorides have one carbon and one chlorine bonded to the CO double bond. The carbonyl carbon atom bears a partial positive charge, and the oxygen bears a partial negative charge. Kinds of organic reactions. In general, we look at what occurs and try to learn how it happens. What includes reactivity patterns and types of reaction. How refers to reaction mechanisms. Addition reactions, two molecules combine. Elimination reactions, one molecule splits into two. Substitution, parts from two molecules exchange. Rearrangement reactions, a molecule undergoes changes in the way its atoms are connected. An addition reaction. These two reactants, ethylene and hydrogen bromide, add to give this products bromoethane. An elimination reaction. This one reactant, bromoethane, give these two products ethylene and hydrogen bromide. A substitution reaction. These two reactants give these two products. A rearrangement reaction. The methyl group move from this position to this position. How organic reactions occur, mechanisms. In a clock the hands move but the mechanism behind the face is what causes the movement. In an organic reaction, by isolating and identifying the products, we see the transformation that has occurred. The mechanism describes the steps behind the changes that we can observe. Reactions occur in defined steps that lead from reactant to product. Steps in mechanisms. A step usually involves either the formation or breaking of a covalent bond. Steps can occur individually or in combination with other steps. When several steps occur at the same time, they are said to be concerted. Types of steps in reaction mechanisms. Formation of a covalent bond. Homogenic or heterogenic. Breaking of a covalent bond. Homolytic or heterolytic. Oxidation of a functional group. Reduction of a functional group. Homogenic formation of a bond. One electron comes from each fragment. No electronic charges are involved. Heterogenic formation of a bond. One fragment supplies 2 electrons, Lewis base. One fragment supplies no electrons, Lewis acid. Combination can involve electronic charges. Common in organic chemistry. Indicating steps in mechanisms. Curved arrows indicate breaking and forming of bonds. Arrowheads with a half head, fish hook, indicate homolytic and homogenic steps, called radical processes, the motion of one electron. Arrowheads with a complete head, indicate heterolytic and heterogenic steps, called polar processes, the motion of an electron pair. Bond making. Homogenic bond making, radical. One electron donated by each fragment. Heterogenic bond making, polar. One electron donated by each fragment. Homolytic breaking of covalent bonds. Each product gets one electron from the bond. Heterolytic breaking of covalent bonds. Both electrons from the bond that is broken become associated with one resulting fragment. A common pattern in reaction mechanisms. Bond breaking. Homolytic bond breaking, radical. One electron stay with each fragment. Heterolytic bond breaking, polar. Two electrons stay with one fragment. Radicals. Alkyl groups are abbreviate R for radical. Example, methyl iodide, ethyl iodide, alkyl iodides, in general, equals Ri. A free radical is an R group on its own. CH3 is a free radical or simply radical. Methyl radical has a single unpaired electron, shown as CH3. Its valence shell is one electron short of being complete. Radical reactions and how they occur. Radicals react to complete electron octet of valence shell. A radical can break a bond in another molecule and abstract a partner with an electron, giving substitution in the original molecule. A radical can add to an alkene to give a new radical, causing an addition reaction. Radical substitution. A radical substitution reaction is a reaction which occurs by a free radical mechanism and results in the substitution of one or more of the atoms or groups present in the substrate by different atoms or groups. The reactant radical react with AB, give a substitution product, and new product radical B. Radical addition. A process by which an atom with an unshared electron, such as a bromine atom, adds to an alkene with homolytic cleavage of the pi bond and formation of a sigma bond from the radical to the carbon. The resulting carbon radical then continues the chain reaction to product the final product, plus another species with an unshared electron. Chlorination of methane, a radical substitution reaction. Steps in radical substitution. 3 types of steps. Initiation, homolytic formation of 2 reactive species with unpaired electrons. Example, formation of chlorine atoms form chlorine and light. Propagation, reaction with molecule to generate radical. Example, reaction of chlorine atom with methane to give hydrochloride and methyl radical. Termination, combination of 2 radicals to form a stable product. Initiation. Under the influence of heat or light, a molecule of chlorine dissociates. Each atom takes one of the bonding electrons. This step produces 2 highly reactive chlorine atoms. Chain propagation. A chlorine atom abstracts a hydrogen atom from a methane molecule. This step produces a molecule of hydrogen chloride and a methyl radical. A methyl radical abstracts a chlorine atom from a chlorine molecule. This step produces a molecule of methyl chloride and a chlorine atom. The chlorine atom can now cause a repetition of step. Chain termination. Coupling of any 2 radicals depletes the supply of reactive intermediates and terminates the chain. Several pairings are possible for radical coupling termination steps. Polar reactions and how they occur. Molecules can contain local unsymmetrical electron distributions due to differences in electronegativities. This causes a partial negative charge on an atom and a compensating partial positive charge on an adjacent atom. The more electronegative atom has the greater electron density. Electronegativity of some common elements. Higher numbers indicate greater electronegativity. Carbon bonded to a more electronegative element has a partial positive charge. Polarity. Polarity is a physical property of compounds which relates other physical properties such as melting and boiling points, solubility, and intermolecular interactions between molecules. Polarity results from the uneven partial charge distribution between various atoms in a compound. Atoms, such as nitrogen, oxygen, and halogens, that are more electronegative have a tendency to have partial negative charges. Atoms, such as carbon and hydrogen, have a tendency to be more neutral or have partial positive charges. Polarity is affected by structure changes. Methanol has weakly electron-poor carbon. Protonated methanol has strongly electron-poor carbon. Polarizability. Polarization is a change in electron distribution as a response to change in electronic nature of the surroundings. Polarizability is the tendency to undergo polarization. Polar reactions occur between regions of high electron density and regions of low electron density. Because of iodine's high polarizability, the carbon-iodine bond behaves as if it were polar. Generalized polar reactions. An electrophile, an electron-poor species, Lewis acid, combines with a nucleophile, an electron-rich species, Lewis base. The combination is indicated with a curved arrow from nucleophile to electrophile. Polar reactions. This curved arrow shows that electron move from B- to A+. A+ is electrophile and B- is nucleophile. The electrons that moved from B- to A+ end up here in the new covalent bond. Water as nucleophile. Water as an electrophile. Electrophiles and nucleophiles. A molecule or ion that accepts a pair of electrons to make a new covalent bond is called an electrophile, from the Greek for electron-loving. An electrophile is the same thing as a Lewis acid. Any molecule, ion, or atom that is electron deficient in some way can behave as an electrophile. Some nucleophiles, electron-rich. Some electrophiles, electron-poor. An example of a polar reaction: addition of hydrogen bromide to ethylene. Hydrogen bromide adds to the pi part of CC double bond. The pi bond is electron-rich, allowing it to function as a nucleophile. Hydrogen bromide is electron deficient at the hydrogen since bromine is much more electronegative, making hydrogen bromide an electrophile. Pi bonding electron pairs can function as Lewis bases. Mechanism of addition of hydrogen bromide to ethylene. Hydrogen bromide electrophile is attacked by pi electrons of ethylene, nucleophile, to form a carbocation intermediate and bromide ion. Bromide adds to the positive center of the carbocation, which is an electrophile, forming a carbon-bromine sigma bond. The result is that ethylene and hydrogen bromide combine to form bromoethane. All polar reactions occur by combination of an electron-rich site of a nucleophile, and an electron-deficient site of an electrophile. The electrophile hydrogen bromide is attacked by the pi electrons of double bond, and a new CH bond is formed. This leaves the other carbon atom with a plus charge, and a vacant p bond. Bromide minus ion donates an electron pair to the positively charged carbon atom, forming a carbon-bromine sigma bond, and yielding the neutral addition product. Using curved arrows in polar reaction mechanisms. Curved arrows are a way to keep track of changes in bonding in polar reaction. The arrows track electron movement. Electrons always move in pairs in polar reactions. Charges change during the reaction. One curved arrow corresponds to one step in a reaction mechanism. Rules for using curved arrows. The arrow goes from the nucleophilic reaction site to the electrophilic reaction site. The nucleophilic site can be neutral or negatively charged. The electrophilic site can be neutral or positively charged. Rule 1. Electrons move from nucleophiles to electrophils. Electrons usually flow from one of these nucleophiles. Electrons usually flow to one of these electrophils. Rule 2. Nucleophiles can be negative or neutral. Rule 3. Electrophils can be positive or neutral. Rule 4. Octet rule. This hydrogen already has 2 electrons. When another electron pair moves to the hydrogen from the double bond, the electron pair in the hydrogen-bromide bond must leave. This carbon already has 8 electrons. When another electron pair moves to the carbon from cyanide minus, an electron pair in the CO double bond must leave. Describing a reaction, bond dissociation energies. Bond dissociation energy, heat change that occurs when a bond is broken by homolysis. The energy is mostly determined by the type of bond, independent of the molecule. The CH bond in methane requires a net heat input of 105 kilocalorie per mole, to be broken at 25 degrees Celsius. Changes in bonds can be used to calculate net changes in heat. Calculation of an energy change from bond dissociation energies. Describing a reaction, energy diagrams and transition states. For a reaction to take place, reactant molecules must collide and reorganization of atoms and bonds must occur. Let's again look at the addition reaction of HBr and ethylene. As the reaction proceeds, ethylene and HBr must approach each other, the ethylene P bond and the HBr bond must break, a new CH bond must form in step 1, and a new CBr bond must form in step 2. Let's see how the addition of HBr to ethylene can be described in an energy diagram. The highest energy point in a reaction step is called the transition state. The energy needed to go from reactant to transition state is the activation energy. A large activation energy results in a slow reaction, because few collisions occur with enough energy for the reactants to reach the transition state. A small activation energy results in a rapid reaction, because almost all collisions occur with enough energy for the reactants to reach the transition state. As an analogy, you might think of reactants that need enough energy to climb the activation barrier to the transition state as hikers who need enough energy to climb to the top of a mountain pass. If the pass is a high one, the hikers need a lot of energy and surmount the barrier with difficulty. If the pass is low, however, the hikers need less energy and reach the top easily. As a rough generalization, many organic reactions have activation energies in the range 40 to 150 kilojoules per mole. The reaction of ethylene with HBr, for example, has an activation energy of approximately 140 kilojoules per mole. Reactions with activation energies less than 80 kilojoules per mole take place at or below room temperature, while reactions with higher activation energies normally require a higher temperature to give the reactants enough energy to climb the activation barrier. The net energy change for the step, delta G0, is represented in the diagram as the difference in level between reactant and product. Since the carbocation is higher in energy than the starting alkene, the step is endergonic, has a positive value of delta G0, and absorbs energy. Not all energy diagrams are like that shown for the reaction of ethylene and HBr. Each reaction has its own energy profile. Some reactions are fast, small activation energy, and some are slow, large activation energy, some have a negative delta G0, and some have a positive delta G0. A fast exergonic reaction, small activation energy, negative delta G0. A slow exergonic reaction, large activation energy, negative delta G0. A fast endergonic reaction, small activation energy, small positive delta G0. A slow endergonic reaction, large activation energy, positive delta G0. First step in the addition of HBr. In the addition of HBr, the transition state structure for the first step, the pi bond between carbons begins to break. The CH bond begins to form. The HBr bond begins to break. Describing a reaction, intermediates. If a reaction occurs in more than one step, it must involve species that are neither the reactant nor the final product. These are called reaction intermediates or simply intermediates. Each step has its own free energy of activation. The complete diagram for the reaction shows the free energy changes associated with an intermediate. HBr, a Lewis acid, adds to the pi bond. This produces an intermediate with a positive charge on carbon, a carbocation. This is ready to react with bromide. Carbocation intermediate reactions with anion. Bromide ion adds an electron pair to the carbocation. An alkyl halide produced. The carbocation is a reactive intermediate. Reaction diagram for addition of HBr to ethylene. Two separate steps, each with their own transition state. Energy minimum between the steps belongs to the carbocation reaction intermediate. Biological reactions. Reactions in living organisms follow mechanisms, with reaction diagrams, too. They take place under very specific conditions. Aqueous environment with a pH close to 7. Temperature of 37 degrees Celsius. They are promoted by catalysts that lower the activation energy. The catalysts are usually proteins, called enzymes. Enzymes provide an alternative mechanism that is compatible with the conditions of life.